Bologna in 2009. From 2007 till 2010, he was in charge of the site selection process for the ELT in Chile and Argentina. Is switch off? Okay. So from the end of So from the end of 2010 till 2014, he was supported astronomical. So he was the support astronomer. Okay, so he was the support astronomer at the Gipun telescope, the UT4, at the Very Large Telescope in Paranal, also being in charge of the continuous monitoring of the ELT plays at Cerro de Armanzones in Chile. Since October last year, he's a support astronomer at the Gran Telescopio Canarias, and his scientific interests are astronomical site characterization, laser-guided star, and adaptive optics. Today he is presenting us a brief talk about the astronomical site characterization in the era of the extremely large telescope, so welcome him.
Okay, this is going to be in English, although I could have given in Spanish, I would have preferred, but okay. I will give it in English. And so thank you for the invitation. This talk is not for experts, it's for beginners, because my idea is to give information to people that doesn't know, people not knowing the argument, the topic, because otherwise, because people working in this topic already knows what we are going to do for this kind of research for the future extremely large telescopes worldwide. So I'd like to start with few slides about history of site characterization, because now we have many observatories in the world, but how these observatories have been chosen, by the way. So in the beginning of the astronomical research, let's say in the 40s, okay, typically observatories were built on national territory, close to the institutions. So it means that the only two parameters taken into account at the time were light pollution and cloud cover. So typically, the observatories were built on high mountains, very close to the cities. Okay, but from the 60s, we had the evolution of the scene concept, means the image blurring introduced by the atmospheric turbulence in the atmosphere. But there were no standardized way to measure the atmospheric turbulence and to measure this final parameter, the seeing, this small number. This became more clear during the 80s, okay, where we had a standardization of the seeing measurements with instruments, and also introducing synoptical parameter in the evaluation. For synoptical parameter, I mean the link between temperature, pressure, humidity, wind speed, wind direction with the image blurring. Okay, so actually, observatories have been chosen on the basis. So first of all, they are in remote places now. They are not anymore close to the cities. They have been chosen on the basis of a number of photometric nights, or at least a number of clear nights. They should have globally, in general, low turbulence, and also for what concerns the global turbulence, in high altitude turbulence that should be much lower for the large to have larger sublatic angles, and of course still far from light pollution. So actually, all observatories are equipped with sync monitoring facilities, cloud monitoring facilities, and also we receive every day or in real time the weather forecast to plan the observations. So I'd like to open a parenthesis now in this introduction, because many of us probably doesn't know how the Earth atmosphere is composed. So probably not all of you knows that the turbulence develops in the first 20 kilometers above ground, not in the entire atmosphere range, so just in the troposphere. Okay, more or less we are between 20 25 kilometers. Okay, so we are interested when we study the turbulence in a site just on what happens in the first 20 25 kilometers. Okay, and also at 90 kilometers above ground, more or less, we have a mesospheric sodium layer that we use in adaptive optics when we want to generate an artificial guide star, so what we call the laser guide star. On this topic, I just open a parenthesis in the parenthesis, it's just one slide, is to tell you that we are conducting now an experiment here in Tenerife at the observatory for what concern a Pathfinder laser guide star facility for the future ELT. And this is a collaboration between the EIC, the Gran Telescopio Canarias, and ISO. So we close the parenthesis in the parenthesis. And so just a little of optical turbulence 101 for people that doesn't know the argument. So the point is that atmospheric turbulence generates optical turbulence. The air, the atmosphere, the air is just a fluid. So it stands under the dynamic of the fluids law. So it means that when we have turbulence, when we pass from laminar regime to turbulent regime, okay, this can be generated by two effects, by two sources. It can be a thermal source or a mechanic source. In the case of a the thermal source, we have a variation of the thermal gradient inversion that erratically change the refractive index of the atmosphere in small spatial scales, okay? Or we can also have a mechanical effect. For example, when the laminar flow of the air encounter an obstacle, for example, okay, like a mountain or a valley in between the peninsula, etc. Okay, so what happens is that a plane wavefront coming from outside the atmosphere passes through turbulent layers and results in a corrugated front. Okay, so but you have to imagine the atmosphere, the Earth atmosphere, like a composition of several bubbles of hairs that forms and disrupt. They decrease in size, they increase in size, and they form again. This is a process, a cyclic process, in which the way these turbulent cells form is well known. They do not form at any size. They're starting to form at the biggest size possible that we know, that we call the outer scale, that for every astronomical size could be between, let's say, 20, 30 meters up to 100 meters. So inside each, can you see the mouse? Okay. Inside each turbulent cell, the refractive index is constant. So here the refractive index is constant. Here the refractive index is constant. But between one turbulent cell and the other, there is a difference in the refractive index. So what happens? That the wavefront disrupt in the transition between two adjacent turbulent cells. But these turbulent cells, decreasing their size with a cascade process, they lose energy or they break in two. Okay, so they become smaller and smaller. So as soon as they lose the energy, they become smaller. So means that we have more area in which we have disruption of the wavefront due to the variation of the refractive index. Okay, so means that a 10-meter telescope like the Grand Tecan, for example, starts to be affected by this effect when the turbulent cells have lost enough energy to reach a size that is smaller with respect to the size of the primary mirror of the telescope. Because here we have just one disruption of the wavefront in this area, you see. But when this becomes smaller, we have different areas in which the wavefront is distorted. But what happens to a 40-meter telescope? To a 40-meter telescope, this effect, this cumulative effect starts much earlier. So it means that the larger the telescope, the worse is the situation for what concerns the distortion of the wavefront. Okay? And the way we use a parameter to evaluate how strong is the turbulence in the atmosphere, we use a structure constant that we call the refractive index structure constant that is not constant at all. It's a parameter that gives you how strong is the turbulent energy with respect to the altitude in the atmosphere. And since the turbulence, so since turbulence phenomenon are aleatoric, we study them under a statistical. We use a statistical approach, okay, to study turbulence. So it's not deterministic, and the effects of turbulence on the image are very easy to recognize. So it's shaking of the image, expansion, and scintillation. So to give you an idea, when you're observing a double star, if you are diffraction limited with your telescope, you just see the 2 points of the two stars. But when you are affected by turbulence and you take an image every few milliseconds, what you have is what we call a speckle. When you integrate this image among, for example, 1 minute, what you have is the sync disk. Is the result of the sum of each speckle taken every few milliseconds, integrated in time. So this is what we call sync, the full total maximum of the results of this effect. And since taking into account the size of a turbulent cell, the biggest it is, the more coherent are two wavefronts coming from two different angles, from two different directions. So less turbulence you have, the farthest you can go to have the same wavefront corrugated in the same way. So this is useful when you're making adaptive optics, multi-conjugate adaptive optics. And but seeing in high altitude is formed by mechanical effects. As you say, for example, the wind speeds at 200 millibars. But locally, when we are close to the ground, the way the turbulence is developing is due to thermal gradient inversions. So every time you have a difference in temperature between two different medium close to the telescope, you have generation of turbulence. So this becomes true, for example, inside the dome, when the mirror has a temperature and the surrounding area has a different temperature. So in this case, there is an exchange of air, so there is air circulation. So this means that we are developing turbulence. And also, this comes true close to the ground, because the ground is heating during the day, releasing this heat during the night. Okay, so this generates again a difference in temperature between the ground and what we call the surface layer that is just above the ground. Okay, so this is what we call a CN square profile. This is a real plot. This is for San Pedro Martir in Mexico, and as you can see, the distribution of the energy of the turbulence with altitude is not continuous. We do not have a continuous. We have well-defined areas in altitude, well-defined altitude ranges in which there is a concentration of the turbulent energy. So this means that the turbulence is developing in well-defined layers. This helps us in identifying which is the exact layer for every site. It's a characteristic of every site in which the turbulence is more strong, in order to conjugate the mirrors of the deformable mirrors when we are making an optic system. And as expected, the strongest layers are close to the ground. So why is this CN square profile important to us? So when we want to simulate the performance of an adaptive optic systems, first of all, we need accuracy. So the more layer we can sample, the better it is. So we are more precise in the estimation of the final corrugation of the wavefront to correct. But also the problem is that you have to you don't want to charge too much the computer that you're using to make the simulations. Okay, so means that you need to model a lot of layers, but enough to be representative and not too many, in order to not make too slow and not to make it too big real-time computing. Okay, so we have done some simulations when I was at ISO a couple of years ago, and it resulted that for the ELT cases, in this talk I talk just about the ELT because this is the project in which I work, but this is the same case also for the TMT, for example, or the Giant Magellan. It will be the same. More or less, to make a good approximation in the simulation, we will need between 30 and 40 layers. Okay, they looks like too much because the computing time it's becoming it's just going beyond the possibility, beyond the fastness that we want. So looks like that when you want do it in real time, if you want to do it in real time during real observation, you have to decrease this number by a factor of 4. So from 30, 40 layers to 10 layers to reconstruct a good CN square profile. So, but why do we want to study this? So this is, I want to show this. Okay, so typically when you have an instrument measuring the turbulence, you are very close to the ground because you build towers that are 6 meters high. So you put your instrument above this tower, so you are 80 meters above ground, and you're measuring the CN square profile in altitude. But typically mirrors of 10 meter class telescope or 80 meter class telescopes actually are placed at are more or less at between 15 and 20 meters above ground. So means that there is an amount of turbulence, okay, that there is an amount of turbulence that I am measuring that is not seen by the bigger telescope. So first of all, I have to find a method to exclude what we call the surface layer, what is below the primary mirror of the telescope. But then, when you're making simulation for a telescope like the Very Large Telescope in Chile, for example, the primary mirror will be much lower than the final position of the primary mirror of the future extremely large telescope. So again, I am making simulation or real-time computing, real-time performance estimations, or an altitude that is affected more by turbulence than the turbulence that will affect in the future the giant telescope. So first of all, we want to know what is the real turbulence at the telescope level. Second, what is the remnant of the turbulence above the primary mirror of the telescope that you want to set the performance of the adaptive optics. And what are the final actions to take into account to mitigate the effect of the atmospheric turbulence in that case. So we have a bunch of instruments to do this. So it's a continuous development of new instruments during these years. So we have many new concepts that are rising in the literature. So to make a citation to all of them, it's quite impossible. So I like to introduce some of them just because they are the most used one in this moment. This doesn't mean that in the future they will be completely ignored and the other ones will be used because they will be found to be better or something. So the most used one actually is not the profiler of the sin square. It's just an instrument that measures the total amount of turbulence in the atmosphere that we call the DIM. That means differentially motion monitor. What the DIM is doing is just to calculate the final value of the energy over the turbulence for the entire range of altitudes. So it's just a number. So it says that above us at this moment we have 10. Okay? The way this energy is distributed in altitude, it's completely black box. Okay? So this is a very portable and easy to build instrument. It's very cheap also. So it's the king of the sync monitoring facilities actually used at observatories for this reason, because it's cheap and transportable. So what you have during your observation when you go to observe at a telescope is the final value given by the DIM. Means that you don't know where this turbulence is distributed, remember. And of course, because of the needings of adaptive optics simulation, new instruments have been built because we need to know where this turbulence is distributed in altitude. Why? Because we want to conjugate the deformable mirrors at the exact altitudes where the turbulence is more strong, where the atmosphere is more turbulent. So for what concern the ground layer, what we call the ground layer, so means the first kilometer above ground, or sometimes you can define it as the first 500 meters above ground, depends on the definition that you want to give. We use what we call the surface layer or the ground layer profilers. Some of them I will go in details later. But for what concerns the high atmosphere, actually the most used one is called MASS. It is multi-aperture scintillating sensor. It's not used because it is the best. It's the most used because it is the cheapest, and this is to transport again. But there are a bunch of other instruments that are, in a way, more reliable and more precise, that can give, apart the low altitude layers, also the high altitude layers. So means that when you combine the turbulence and in high resolution from the ground layer profilers with the sin square profile from the high altitude profilers, and you normalize to the value given by the instrument that is not a profiler but give you the final number, then you can reach your goal, that is understand the distribution of turbulence in the surface layer, in the ground layer, in the mid atmosphere, and the high altitude atmosphere. So it's a combination of data from different instruments. The point is that the perfect instrument doesn't exist because, for example, in the case of the profilers of the whole range of the atmosphere, they do not reach enough resolution in the ground layer, for example, in the low atmosphere, where you want a resolution of about 10 meters. They can reach a resolution of a few hundred meters sometimes, but this is not enough when you want to know what happens between your 8-meter towers and 15 meters where your primary mirror is placed. So in this case, you need much more resolution. Okay. So to explain you this is much more clear now. You have your instruments that are placed at different altitudes, okay, above ground, but typically between 1 meter, 6 meter, 8 meters. But then you want to know what happens above the primary mirror. So you want to know what is the remnant of what we call the ground layer, okay? But then also you have to take into account that different profilers are placed at different altitudes. So when you want to merge information from different instruments, you also have to take into account that they are at different altitudes. So it means that you have to merge data taken at different position from different instruments that uses different techniques. And when you have to merge them, you reach something like that is an approximation of the probability that the CN square will have that profile. Because, again, it's a statistical analysis that we are doing. So I just go fast in this because the level of attention of people is decreasing with time exponentially. So we focus now in the ground layer and in the free atmosphere. I will introduce just 4 instruments that are the most used at the moment. Again, I repeat, doesn't mean that in the future they will be ignored and the better instrument will come in the next few years. So this is a profiler for the ground layer or the surface layer. It is called the SLODAR. SLODAR stays for slope detection and ranging. So what happens is that this instrument is looking at a double star target, okay? And it uses a triangulation method to observe this double star target on a Sharp-Hartman wavefront sensor. Okay, so the number of sensor layer depends on the number of the subaperture of the Sharp-Hartman wavefront sensor, and the spatial covariance of the slope of the wavefront phase aberration is measured and gives finally the information of the CN square. Okay, we have a classical version in which we use a Sharp-Hartman with 8 subapertures, so we have 8 layers starting from the ground with a resolution of 100 meters, but still this is not enough. So a new version has been developed by the University of Durham that is called the surface layer SLODAR, in which the separation of the binary is very wide, so we are above 100 arc seconds. So the resolution increase up to 10 meters. So every 10 meters we have information about the distribution of the CN square above the ground. So it's a high resolution profiler, but it requires telescopes of about between 60 centimeters primary mirror and the emitter. So this is not cheap and this is not transportable. So if an observatory decides that wants an instrument like this for monitoring the turbulence in the ground layer, means that they really need it for some purposes. It's not just an instrument that you install just for monitoring. This is a picture. This is a real picture of the surface layers that are installed at Paranal. There are many of these prototypes in other observatories. They have been tested also at the Roque de los Muchachos. They have been used also at Mauna Kea. So I have pictures of ISO just because I was at ISO until October. So this is why. And another profiler for the low. This is the other face of the coin. We say in Italy. So la otra cara della moneda. No? This is another profiler. This is conversely to the SLODAR. This is very cheap and transportable. It's just a small box like this, but this is less precise. Okay, and this is a lunar profiler. Yes, it's a lunar profiler. It's looking at the moon, at the light scintillation coming from the moon in 6 different photomultipliers that are here. We have 6 photodiodes, not this, the two one at the extremes, the one in the center. Okay, this is difficult without the mouse. Okay, this one. So what happens? That the light, the scintillation of the moonlight, it arrives to the different multipliers and it's projected with cones, right? So when the 2 cones overlaps, we have correlated signal. So it means that at that point we can understand what is the CN square at that altitude, because we have correlated signal because from 2 different light cones that are measuring the fluctuation of measuring the scintillation of the light moon along the moon diameter. The problem of this instrument is that, for example, it can work only just 10 days per month, because it is reliable only when the moon illumination is above 80%. And it's optimal when you want to go in remote places, because you just transport it in your backpack, for example. Okay, but again, since the light cones, they are just 6 light cones, at the end, when you make the combination between different light cones, the maximum altitude that you can reach is 250 meters above ground. So the CN square profile is reliable only up to 250 meters, because otherwise the 2 cones, the overlap of the 2 cones becomes too weak, because the two very distant cones are overlapping at very high altitude, but with a low section, with a small section. So the final value of the CN square that you have at that altitude is not that reliable. And we wanted to see what are the limitations of these 2 instruments, because we had the opportunity to observe with both of them simultaneously for tens of nights during 2011, 2012 at Paranal. So we have taken simultaneous measurements under different conditions on wind speed. Because when wind speed is not enough, means that it is very low, the turbulence has no way to develop. You need a minimum wind speed to let the turbulence develop. When you want to pass from laminar regime to turbulent regime, standing under the law of Kolmogorov means that the turbulence power spectrum in 3 dimensions has a slope of minus 11 thirds. And what we've done is to compare the total CN square at a fixed altitude ranges, okay, from the two instruments. And we indeed have found that the two instruments diverge a lot when the wind speed is lower than a certain limit that we found to be 3 meters per second, but maybe with more values, with more measurements, we could have been more precise. But I say that there is a limit in wind speed. So it means that, for example, independently on the instrument that you use, you cannot use data, or you cannot rely on data of this, coming from these instruments when you are in very low wind speed regimes. So this is another limitation that we have when we want to reconstruct the CN square profiles for a site. Okay. For what concern now the high atmosphere, so now we pass from the low grounds to the high grounds. So sorry, to the high atmosphere. I will present to you the two most common used instruments at the moment, that are the multi-aperture scintillation sensor and the generalized SIDAR technique. For what concern the mass, this is again cheap, light, and transportable. So again, there is this comparison, but low resolution. This instrument uses, this is a real picture coming from Armazones, by the way, from the site of the ELT. So this instrument is observing a single star target, not double star, a single star target. And the light scintillation is measured by 4 concentric annuli here. So, I don't know where the mouse is, sorry, okay. So we measure the difference in scintillation between the two, between pi pairs of concentric photomultipliers. And this yields information on the vertical profile of the turbulence in the atmosphere with a resolution that goes with a 2 to 10 logarithmic scale in altitude starting from 500 meters above ground. And this means that the resolution of the instrument is decreasing exponentially with altitude. And you can see that we just have 6 layers in the high atmosphere, but the higher you go, the less is the resolution. At a certain point, you don't know where the turbulence is distributed, for example, between 8 kilometers and 16 kilometers above ground. So this is because of the mass weighting function, because since we are using information coming from pairs of photomultipliers, the peak of the weighting function corresponds at the altitude in which the pairs of photomultipliers have the maximum sensitivity. So we do not have information on the total on the distribution of the turbulence inside this weighting function. We just say that the entire area contains a certain amount of energy, but we really don't know how the turbulence is distributed among these altitudes. So it means that again, we do not have enough resolution, and but for some purposes this could be enough. On the other hand, this I thanks Jesus for the image, because this comes from from him. So on the other hand, I don't want to go too much in details. Other techniques allows to have better resolution in the high atmosphere, okay? But we have to sacrifice the price to pay to have this kind of more precise instruments, or the transportability, because instruments like the SIDAR, for example, needs telescopes with diameter higher that to be no less than 1 meter, for example. Okay, so what we want to understand when using different techniques is what is the best for our purposes. Okay, so the best is in this case again to compare two different instruments measuring the same quantity, and to see how do they correlate, okay, independently of their resolution. So we had the opportunity to use a SIDAR for 14 nights more or less, for 2 weeks at Paranal in 2007, we used the generalized SIDAR developed by the AIC. It was a twin of the other two generalized SIDAR used at Teide and at Roque. Okay? And with a 300-meter resolution in the high atmosphere, we had the possibility to measure also with a mass in Paranal simultaneously to the generalized SIDAR developed by AIC. What happened is that we were aware that previously in 2005, there were a warning concerning the usage of the mass instrument, because when compared to another generalized SIDAR used at Mauna Kea, the authors found a strong discrepancy, because when you extrapolate the turbulence from the SIDAR in the same altitude ranges seen by mass, okay, you should find something similar. So if I have a layer seen by the mass between 10 kilometers and 12 kilometers, and I take the turbulence seen at between 10 kilometers and 12 kilometers by the SIDAR, I should have more or less the same amount of energy. I should have more or less the same number, within 20% more or less. This was not the case when there was a direct comparison at Mauna Kea. So using the data at Paranal, I was co-authoring this paper, although I was not agreeing 100% with the method used. We found, again, strong discrepancies between the two instruments, but differently with respect to the previous study. Because, for example, if you see here, in layer number 2, for example, between 500 meter and a kilometer, we see that the mass, for example, is underestimating a lot the turbulence with respect to the SIDAR. Okay? And that was not the case, for example, when the study in 2005. So there is something that is happening. Why? The point is always the same, the number of data that you have, because the more data you have, the more reliable is your statistics. And then on that case, they just used data for a few number of nights. It was 4 nights only. We had the opportunity to measure for 2 weeks. But again, we think this is not enough. But the point now is that here you have some numbers. So when we look at the relative error of the turbulent energy measured by the two instruments, so this is these are the numbers coming from the generalized SIDAR, these are the numbers coming from the mass. For what concerns the turbulent energy, for some layer we have a relative error that is really scaling. So it means the two instruments do not agree at all. So one of the two is wrong. So we have reason to believe that the wrong is the mass, not the SIDAR, because the SIDAR is more reliable technique that has been used for many years and has been proved by many teams all around the world. But the final point is that the community is using mass data since 2004. So there was really an issue in the last 2 years, because mass data are used actually to make to provide CN² profile for adaptive optic performance simulations. And what we have to focus in is that we need to be pragmatic. So we have, for example, data since 2004, and we need to use them in some way. So we need to understand the limitation of this data. And so we don't want to prove any of the two techniques. We need to use the data, just that, okay? So first point is that data from the two studies are compared in linear regression. So one of the suggestions was that linear regression is not good, because when you have high outliers, they are pushing the regression toward the orientation. So probably it's better to compare that in log-log. So this kind of tricks to understand what are the real, how the data correlate for real between them. So also the mass has a triangular weighting function, and we have no idea on how many CN² is among the same area. So the geometry of the weighting function of the mass are not good. They are not. I mean, what I want to say is that they are not compatible. I'll say the word is right in the presentation. So they are not compatible with the simulation of for adaptive optics. So the idea is that to switch, for example, from triangular weighting function to rectangular weighting function. This means apply some mathematics on the data, but is a proposed solution. So we have submitted a paper recently on this, just to face the issue, because again, we don't want to prove any of the techniques. We just need the data. And we have data since 2004, so we have more than 10 years of data, and we need to provide numbers to the teams that are developing adaptive optics simulations. So So it's again, we want to merge data coming from Lucy or the slaughter, and then to put them together with data coming from the SIDAR and the mass, and then we want to normalize with the DIM, and all of the instruments are giving different numbers. So it's not easy, because again, it's a statistical analysis that you make on the turbulence. So you will never have two instruments agreeing 100%. So we're happy when two instruments agree by 20%, more or less, okay? But we are not agreeing even by 20%. So it's if we want to make some preliminary conclusions, is that there are no conclusions. There are no conclusions, really, there are no conclusions. And it's a continuous work in progress. And I told you already that the perfect instrument doesn't exist. And because, again, I told you already, I anticipated, we need to merge information from different instruments, having different resolution, to have enough resolution for our profile. So what has been proposed recently is to make a big cross-comparison campaign in which we use the most known instrument, I mean, let's say 10 or 8 or 12 of them, to go somewhere, for example, here at Teide Mountain or at Roque or at Paranal or Mauna Kea, I don't know, the most exotic location you choose, and to measure with all of them together in seasons, means during summer, during winter, during spring, during fall, because the atmosphere is behaving differently for every season, because it is connected to the synoptical parameters, the turbulence. And so new instruments are at the horizon right now, they're rising, and we hope to have some information about some of them, for the next SPI conference next year, for example, from the stereo SIDAR, for the people that knows this technique. And we know that there is much effort is required for the purposes of giving enough resolution for the square profiles that we provide to the optics community. That should have been the end of the talk, but since I have 10 more minutes, I want to. Okay, I just give 10 minutes. May I? Now it's not for beginners. Now is for experts. We want to show to 3 or 4 people here that is in the topic. I would like to show how are we merging. So how are we working with this data, passing beyond the problems, etc., and how we merge the profiles. Okay. So again, if you remember, this was a bunch of instruments that I presented before, but now I just take the ones from which I have more data. So the lunar scintillometer, that was the one that I had on my backpack together with another guy in this room a few years ago, and to merge the data with the mass, normalize the data from the two instruments on the total CN square value that I have from the DIM, and finally have my CN square profile. So I told you why to use Lucy and mass, because first of all they are the biggest database that I have at this moment for the sites in which I am making the study. And how I will do that? I will merge the profile from Lucy and mass, and I told you already, and normalize with the DIM. So means that when I sum the total turbulent energy from mass and ground layer, I should have the same value of the DIM. That is not the case, but I will show you. And what happens is that Lucy, remember I told you that there are light cones, okay, looking at the moon scintillation. When they overlap, okay, in the area in which they overlap, we have correlated signals. So this fixes pivot points. So at each pivot point, I have a value for the CN square. So it means that if I want CN square value in between two pivot points, I have to interpolate. Okay, so this is what we do when we want to increase the resolution of our profile. Theoretically, infinitely we can do it. We can do this, but and we will stop at a safety altitude, in which the light cones, the overlap of the light cones is the area of the overlap of two light cones is too small, and so it means that the CN square value is too much biased, and we cannot believe in it. So we will stop more or less at 350 meters in altitude for what concerns the ground layer. So what happens here is that I just taken all my data, and data from Lucy, so these are the 4 pivot points, and data from the mass. Okay, so if I merge them just with median optical turbulence profile, I have this CN square value, So the mass is not corrected, means that when I make the comparison with the CIDR, I found some difference. So what I do in the correction is that I normalize the value of the mass on the data of the CIDR, just to have. So I found some multiplication factor that I apply to every layer of the mass to have a one-on-one comparison with the CIDR. So in this plot, I have not corrected any of the layers of the mass. What happens is if I sum the turbulent energy from the mass and Lucy, I see when comparing to simultaneous the measurement that I don't reach this turbulent energy. Means that I have a lack of turbulent energy somewhere. So some instrument is underestimating the amount of turbulence. Is it Lucy? Is it the mass? So first of all, I have a gray layer, which I don't know where to put this turbulence. I have some turbulence that is somewhere that I'm not measuring. So where do I put it? In a gray layer in between is not physical, okay? So this is not possible. So what I do is that I correct the mass. I can correct the mass. So the blue line is the mass corrected after comparison with the CIDR. So I found some multiplication factor. But again, I still have some missing turbulent energy. So what I understand is that also the lunar scintillometers, since it's based on the same technique as the mass, more or less, is underestimating, because probably is a weakness of the technique, is underestimating. So what happens is that I normalize the measurement from Lucy to the amount that is dim minus mass. This is totally arbitrary method. It's totally arbitrary method. So, but at least it's something. We have an idea on the shape. Okay, so this was my starting point, the red lines, and this is my final point, the blue lines. So I can retrieve the median sin-square profile at different single ranges, for example. But again, there is something that this is not a typical shape for the sin-square. There should be a continuous with some bumps somewhere because the energy is distributed in fixed layers. But this layer here still is, where's the mouse? This layer here is still not really physical. I mean, it's not as it should look like. So for sure we need to refine the method. And there are different teams worldwide that are trying to treat this data. There are no real solution at the moment. This is the limitation that we're facing. Is what we have, is nature, is the instrument, they have the limitation. So the final message, so I finish now. My final message is that we cannot really give final precise answers to the whole community until we make this cross-calibration campaign, and probably we take more into account different biases that the instrument can undertake. Okay, thanks.
Thank you so much, Gianluca, for this very interesting talk. We have some time for questions, in case you have any of them. No questions? Okay, so let's thank again Gianluca.